do I use DWT repeatedly? Well, fortunately not. There is a function called wave decomposition, wave DEC, and if you look up the syntax, it says it performs multi-level 1D wavelet decomposition, and you have to pass the signal x, specify the levels level of decomposition that you want to go down to, and of course the wavelet name. Alternatively, you can also specify the low pass and high pass filters. How do you get the low pass and high pass filters? Well, there is a command called W filters, which gets you the filters associated with these different families. For whatever families the filters exist, the W filter will be able to get you the filter coefficients, Dobeschi, Coiflet, Simlets, or if you want to use biorthogonal wavelets or reverse biorthogonal wavelets and so on. So, for example, if I want the filters associated with the, that is analysis and synthesis filters associated with Dobeschi 2, then I use this syntax, say dB2, and you can see it has given me the h of n, that is low underscore d, high underscore d, which is g of n, and low underscore r is the low pass filter, reconstruction low pass filter. But we have already seen these filters are orthogonal wavelets, therefore, the synthesis and analysis filters are going to be identical. Therefore, low underscore r is actually what it has done here is it has given me a reflected version. In fact, there is a slight reflection there, g tilde of n is not exactly g of n, but reflected version, and that is what you see here, and high underscore r is a reflected version, because when you implement, you will have to implement with the reflected versions, and that is why it has given me that. But you can verify if these filters satisfy the conditions here. For example, if they have been designed correctly, the sum of the filter coefficients should be √2, and that is what it is for the low pass filter. For the high pass filter, what should be the sum of the coefficients? It is a high pass filter, therefore, the sum should be 0, because g of omega should be 0 at omega equals 0, and g of omega at 0 frequency is nothing but the sum itself. So, if I look at the sum of, it is 0 up to a working precision, right. So, you can verify this for other filters as well. Now, let us get back to the wavelet decomposition. We will not supply the filters, we will directly specify the name of the wavelet that we want to use, and we shall use again the Haar wavelet here to just for the purpose of demonstration. So, now what does wave DEC return? It returns the coefficients and a vector or an array called L, denoted L. What does this L contain? First of all, what does this vector C contain? It contains a vector of coefficients arranged in the order that I had described in the previous lecture. If I perform a 2-level decomposition, I have A2, D2 and D1. So, it is going to arrange in the sequence A2 followed by D2 followed by D1, and if the signal is of length n, A2 will have a length n by 4, D2 will have a length n by 4 and D1 will have a length n by 2, and those lengths are given returned in this vector L. Okay. So, let me show you that here. So, let us say I get this CAD, that means essentially it contains the approximation and detail coefficients, and L, and I perform a 2-level decomposition here of the signal. So, I have done that, and now let us look at L. So, what it has returned is 64, 64, 128 and 256. Now, what has happened here? Why is it giving me 4 whereas I performed whereas there are only 3 scales here? The last one corresponds to length of the signal. Okay, the last number in L corresponds to the length of the signal. So, strictly speaking only the first 3 are of interest to me, and let us look at the CAD. Okay. CAD is a big vector of length 256. Naturally, I have 64 plus 64 plus 128. So, when I plot here, now I would like to plot of course, the signal and its coefficients. Let us go through this a bit tedious exercise, but we will still do it. So, we will plot the signal, and then I have subplot 4 and 2 where I will plot the approximation coefficients, and here we will say stem once again 1, 2, not 2 anymore, because now the resolution has fallen by a factor of 4. So, 4 to n, and what do I want? C of 1 to L of 1, because L of 1 tells me what is the length of the first set of coefficients, and let us plot this in red, and oops, sorry, CAD. So, let us see if the plot is coming out all right. So, let us plot the next coefficients, and here it should be L of 1 plus 1 to L of 1 plus L of 2. Those are the coefficients I require, and the resolution for D2 is also n by 4, and we shall use a green color for this. And finally, in this case the resolution D1 is at a resolution of 2 TS, right, and here I shall use L of 3 minus 1, L of 3 is 128. So, 120 sorry, L of 3 plus 1 128, L of 3 plus 1 2. Luckily, I have the signal length stored in the last element, and that is L of 4. Oops, so, let me use another color here. Let us use a cyan color. So, now I have all the coefficients here. So, on the top I have the signal, and in the second panel I have A2 at a resolution of T by 4, but sampling interval of 4 TS, and detailed coefficients D2 at a sampling interval of 4 TS, and detailed coefficients at the first level. These are the same that we have seen earlier. D1 does not change. What has changed is now A1 has been split into A2 and D2. Now, these are the decomposition and the approximation and the detailed coefficients. In fact, something interesting, the DWT has a nice property that it preserves the energy of the signal. What does it mean? That if I sum square these coefficients in each of these bands and add up the energies of the coefficients in each of these bands, I should recover the sum square of the signal itself. So, let us see if that is true. So, let us ask for, so let us say A1 SQ, so this is A2, right. So, A2 SQ so, this is the sum square of the approximation coefficients in A2, and likewise D2 and this is how the sum square, this is the sum square of the D2 coefficients, and finally we have D3, sorry D1. So, this is what I have for D1, and as you can see the sum squares are decreasing. What does the sum square tell me? It tells me, it gives me an idea of the energy contained in the signal in that frequency band. Each scale corresponds to a frequency band. Approximately these frequency bands are 0 to 1/4 of the Nyquist frequency, sorry 1/4, yeah, 1/4 of omega max, and then 1/4 of omega max to half of omega max for D2, and then half of omega max to omega max, which is Nyquist frequency for D1. So, this clearly tells me, if I were to simply draw these numbers in just as a stem plot, you can see that. So, these are the 3 points here. Let me actually make it more visible for you. Let me set the x limit such that you are able to see. The plot clearly. The first spike here corresponds to the sum square of the A2, and the second corresponds to the sum squares of D2, and the third here corresponds to sum square of D1. It is very clear that most of the signal's energy, first of all, as I told you, the sum of these three should get me the energy of the signal. Let us quickly verify that and come back to this figure. So, the sum of A2, this is the sum square of the A2 square plus D2 square plus D1 square, and now let us add up, right. So, what we have shown is the energy is preserved. In other words, if x is your signal, it is a vector. So, sum square of this x is, if you have performed L level decomposition, then it is AL, the sum square 2 norm of AL plus the square 2 norm of AL plus the sum square 2 norms of the detailed coefficients of I equals L to 1, or you can say 1 to L. I just went from L to 1, so that when you expand this, you will get dl first and then you will get dl minus 1 up to d1. This is a very beautiful way of decomposing the energy of the signal into the respective frequency bands. Of course, this was even true for the Fourier case we have seen by virtue of Parseval theorem, but this is nice also because now I am able to collect the frequencies into a single band, and now I know clearly, at least for this example, where we have chosen L to be 2, we have seen that 80% or more than 80%, in fact we can get the exact number, a significant fraction of the energy is solely contained in the approximation coefficients, right. How much of the energy is contained in the A2 alone, that is the frequency band 0 to omega max by 4. I can clearly do that. I can say, well, I can compute the fraction here, A2 square (95.4%) of the signal's energy is contained in this frequency band. Now, for those of you who are familiar with principal component analysis, this is similar to principal component analysis for a single signal, where we are decomposing the signal's variance or energy into different bands which are non-overlapping, which are orthogonal. Even in principal component analysis we do that, but in the multivariate sense, where we decompose the variance or the covariance of the signal of the set of multivariate signals that we have into into what are known as principal components, and the variance of the total variance of the multivariate signals can be expressed as the sum of the variances of the principal components themselves. So, that is the similarity here. What is PCA for multivariate signals is DWT for univariate signals in that sense, and many researchers have exploited this parallelism between PCA and DWT and written quite a few nice articles on that. So, now why is this information of use to me? Where can I use this information? Let us go back to the plot here. This plot of course clearly tells me that I can really work with the coefficients in A2 alone, right. So, if I look at this plot here, how many coefficients do I have in A2? In the signal I had 256 coefficients, in A2 I had 64. Now, I know that A2 contains 95.4, let us say for discussion 95%. 95% of the signal's energy is contained in these A2 coefficients, which are 64. From a signal compression viewpoint, this is excellent. If I am willing to go for a lossy compression, then I need to store only these A2 coefficients, which is 64, whereas the original signal is 256 numbers long. Therefore, I have achieved a compression factor of 4. So, suppose I adopt that compression strategy where A2 will now be used instead of the signal, then of course, it is a lossy compression, but if I recover the signal from A2 alone, do I miss out on any key features? Obviously, I am going to miss out on some features, because if you look at the plot here, what I am doing is I am really throwing away D2 and D1, and the information contained here due to the spikes may be lost. Not completely though, but depending on how these features are important to you or not, you can treat them as significant, but a part of the information contained here at these spikes will be lost, and we would like to know how much of it is lost. How can I know? Well, what I do is I just reconstruct the signal from A2 alone, and that would tell me what my compression has actually lost out on, right. And let us do that. Now, that part here is implemented by Wave REC, which performs a multi-level wavelet reconstruction. Of course, if you supply the coefficients that you have obtained straight away to Wave REC, it will recover the full signal for you. But what we are saying is, I will only store A2 from a signal compression viewpoint, and I will ask what kind of a reconstructed signal I would get, and then I will have an idea of how good the compression is in terms of restoring the original signal, how much loss has occurred. So, for this purpose, where let us say CAD has modified to some threshold, it is as if now I am applying a certain threshold. What I am doing is I am saying all the coefficients in a certain scale are going to be 0. Which scales? D2 and D1. So, I am going to set here, first of all I am going to create a new CAD, the coefficient vector, to this, and then in this I am going to set all the coefficients from 65 to end, that is whatever is there in D2 and D1 to 0, all right. And then I am going to use this for reconstructing the signal. So, let us call it as x hat. The thresholding here that is being done is called a scale based thresholding. What I have done is I have just discarded coefficients simply over certain scales. Very quickly we will learn what is known as an amplitude based thresholding, where I will perform thresholding, I will retain or throw away coefficients depending on their magnitude. Okay. So, CAD threshold here is being supplied, and also what it requires is the length of the coefficients and the filter that you used for decomposition. Obviously, you have to specify that, and I have my x hat. So, now let us plot here in this figure let us plot both the signal and the x hat, and let us force them to column vectors and see how good they are. Let us have line width 2 or even 3 just for better visibility. So, what has happened here? The blue one is the original signal and the red one here is the reconstructed signal, that is the signal that you have recovered from its compressed version. The compressed version was 64 coefficients contained in that A2. So, we have recovered most of the signal for sure. Now, you have to ask whether, so if you look at these points as expected, the sharp points have been now flattened out quite a bit, and they are flattened out differently because each of the sharp points have different features. Some of these have strong features in D2 and D1 and some of these have mild features in D2 and D1. Therefore, the signal has been reconstructed with some different errors at these different points. Now, whether this is important to you or not depends on the application. If you think that the sharp points are due to outliers, due to some faulty sensing, faulty sensors, then you are willing to let go. But if you think that the sharp points carry valuable information about the process, then you may have to store D2 also with A2 or D1 also with A2. So, now there you can start seeing the number of combinations that you can think of in signal compression, but hopefully the basic idea in signal compression has been conveyed to you. And in this process we have also looked at discontinuity detection. Now, let us actually quickly ask what an amplitude based thresholding would do. An amplitude based thresholding, as I explained earlier, would threshold the coefficients, that is zero out the coefficients which are below a certain threshold in magnitude, right. That is the idea of the amplitude based thresholding. And then there are variations in that. Some estimation or some compression algorithms, the basic idea in compression estimation is the same. For example, here we discussed it from a signal compression viewpoint, that D2 and D1 can be thrown away because they contain insignificant amounts of energy. If I am a person who is working in signal estimation, I can treat D2 and D1 as due to some unnecessary features in the signal, undesirable features. This could be due to noise or whatever. In that case, throwing away D2 and D1 amounts to throwing away noise, and I know already that this is what is the noise characteristic. So, I should know a priori what are the signal and noise characteristics roughly, and then I apply a threshold. Once again I have applied a scale based thresholding here, but I could apply an amplitude based thresholding, and as I said, in amplitude based thresholding there are different flavors. I can say that I will not touch the approximation coefficients at all because they contain the global features of the signal, and I will only apply threshold to the detail coefficients, and within this there are different variants and so on. So, the number of different types of combinations of this vanilla idea is just enormous, but the basic idea is perform a decomposition, apply thresholding and then recover the signal. In compression you do not recover the signal, you only store the coefficients, you only recover when it is needed. In signal estimation you do recover the signal, that is the primary difference. And of course, the objectives are also slightly different, it makes a big difference. In compression, I would like to recover the original measurement as much as possible, whereas in signal estimation I would like to recover the true signal. Okay. So, let me just explain that to you on the board. So, I assume that I have a measurement y which is made up of two components in signal estimation, where x is the signal and v is some kind of a noise and y is the measurement. So, in signal estimation my goal is to recover x, whereas in compression I would like to recover y as much as possible. So, the objective is different, but the principle is the same. in compression and estimation both, what I am going to do is perform a wavelet decomposition of y and then apply thresholding. Then the difference is in how you apply this thresholding. In signal compression, I would like to, the goal is to store the signal in as many few coefficients as possible, while still minimizing this norm here. Okay. In fact, let me say here y minus y hat, where y and y hat are vectors. Y is the measurement vector, y hat is the recovered vector that from your compressed version. This is the compression objective. In estimation, the objective is this. Of course, the big difference in estimation is I do not know what is x. Of course, there are, then you can show that when you adopt a certain estimation algorithm, what kind of norm value do you get and so on. But as you can see, the compression goal is different from the signal estimation, but both use the same algorithms, right. So, I have shown you how signal compression is done. You can add noise to x and then repeat the same exercise, and I have shown you how scale based thresholding is done, but you can repeat the exercise with an amplitude based thresholding. I am not going to show you the amplitude, how to perform the amplitude based thresholding from the command line. Very quickly, let us go through the menu, the GUI that the Wavelet toolbox comes with, which will allow you to play around with a number of different thresholding techniques, and I am just going to show you a couple of examples here. Okay. So, let us bring up the GUI, which is brought up by typing wave menu, and we have seen this before. Now, we pick wavelets 1D. By the way, if you want to simply have a display of wavelets, you can go here and get the display of wavelets, but right now we are interested in DWT. Let us pick the one dimensional wavelet transform, and one thing that I strongly, very strongly recommend is to you to go through this many examples that this toolbox has. There are a number of examples that you can work out with. It is obviously impossible for me to go over all of this, but let me show you here how to import the signal from the workspace, and we would like to actually import this signal that we have generated. So, this is a signal that we have generated, and now we would like to perform DWT. We have performed a Haar wavelet analysis. So, the default here is Haar. On the right panel, you can choose the wavelet and the levels to which you want to perform. So, we have chosen the Haar wavelet, and I performed a 5 level decomposition, but to generate the same thing that we have seen here earlier, we have performed a 2 level decomposition. Now, a big caution here, which is the notation that is used here. Unfortunately, the notation that is used here is inconsistent with the general literature. The small a, small d and the small d's here are not the coefficients, unfortunately. They are actually the reconstructed signals themselves. Okay. And if you want the coefficients, then you go here. There are different ways of looking at the decomposition. That is a very nice feature here. You can look at a full decomposition. By the way, how do you know that these are reconstructed components? Well, look at the top. It says the signal S is a sum of A2 plus D2 plus D1. And that is only true if these A2s, D2s and D1s are reconstructed components. You cannot add the coefficients. So, it is clear that these are reconstructed signals. Reconstructed signals are to be treated as filtered signals, but for most of the analysis that is done in the literature and applications in the literature, normally one works with coefficients, not the reconstructed signals. Okay. In fact, the energy decomposition that we wrote was for the coefficients, not necessarily for the reconstructed signals. So, you have to keep that in mind. So, how do I get my coefficients? Well, to a certain extent you can get that by going to the last option here, where it shows the reconstructed signal in a particular band and the coefficients here sorry. So, the bottom one here shows the detailed coefficients. In fact, again the problem there is that it shows magnitude of the detailed coefficients, it does not show the absolute coefficient. So, some of the features of this GUIs are not so user friendly, unfortunately, at least in this version, but some of them are. And if you want to do a manual analysis yourself, then you can do a export. For example, you can export to the workspace the coefficients, okay, and then you can work with those coefficients. But the nice thing here is, of course, I can do a compression and I can do a denoising. So, for example, hitting on the compression tells me how changing the threshold will change the energies and so on, and I ask you to explore this option. Let us quickly look at the signal estimation. So, the estimation part here is obtained by denoising, all right. Now, what is happening here? What is this plot showing me? Well, it is showing me the thresholds that it has calculated. How are the thresholds calculated? There is a procedure, there is a very extensively studied piece of work, that is how thresholds are to be calculated. The basic idea, as I said, is take a threshold, apply it to the coefficients in each band, and there are again two versions there. One version which is called hard thresholding, what it does is, if it finds that if the magnitude of the coefficient is below a threshold, it will set to 0 or retain the coefficient as is. The other procedure, known as soft thresholding, will not only reduce the coefficients to 0 that are below the threshold, but also shrink the coefficients that are above the threshold by the magnitude of the threshold itself. That is called a soft thresholding, and that is called shrinkage. So, there are these two versions, hard thresholding and soft thresholding, and those are the two options that you see here, hard thresholding and soft thresholding. The default here is set to soft. Both have their disadvantages and advantages, and I will quickly talk about it in the short lecture that I have after this. It is just a summary of what we have discussed. So, you can now choose different thresholds if you want. It is applying the same threshold. How did it calculate the threshold? I will tell you how it calculated the threshold. There is something called a universal threshold that is given out by Donoho. Thresholds are typically denoted by lambda in wavelet literature, and it is given as sigma times 2 root of 2 ln n, where n is the length of the signal, and sigma is the standard deviation of the noise that you have, all right. How do you estimate the sigma? Obviously, I do not know upfront. This is known as a universal threshold. This sigma is calculated based on the energy of the detail coefficients in the highest frequency band, okay. And there are again variations to that idea, but if you consider the noise to be primarily in the high frequency band, then the energy contained in d1 square would be an estimate. So, sigma hat square is nothing but this itself. This is a crude estimate of sigma square, and the square root of this will give me sigma. This is assuming that the noise is white. What we mean by white noise is uncorrelated noise in time, and that primarily the noise is in the high frequency band. Then there are variants for this depending on whether the noise is correlated, the structure of the noise, whether it is colored noise and so on and so on. So, we are obviously not going to go over that extensively, but this is the basic or you can say seminal work in thresholding based methods. It is called a universal threshold, and what is done is, in hard thresholding, if any coefficient in at a certain scale at a certain level, if this is less than lambda, then dm is set to 0. This is hard thresholding, and you can apply this if you need to the approximation coefficients as well, but normally one does not touch the approximation coefficients because that is believed to be containing the signals features. But you can apply, there is absolutely nothing preventing you from doing that. In fact, that is how different PhDs and master's thesis are born, trying out different options. And this is the hard thresholding, and the soft thresholding, what it does is it in addition to this, it says for those which are, when I say dm here, in fact all the coefficients at any scale m. Okay. So, you should understand, in fact dm 10 d, you can think of it this way. So, for those coefficients which are greater than lambda, they are set to dm minus lambda magnitude. So, they are shrunk to this. So, dm minus lambda, well in magnitude they are shrunk. Okay. You can say that first the magnitude is taken and mod dm is modified to this, and then the sign is retained. Okay. So, they are shrunk by that magnitude. This is called the soft thresholding, and then how you apply these thresholds is a thing. So, first step is decomposition, the second step is computation of threshold, and the third step is how you apply this threshold. Do you apply this threshold to every scale or to only select scales, to half of the scales? There is something called interval thresholding. I will just quickly go over an example on interval based thresholding and so on. All of that depends on your signal and noise structure. The basic idea, however, is the same: perform decomposition, determine the value of the threshold, and choose a thresholding method. And when you have different combinations of this, then you have at least about 20 to 30 different thresholding methods, and there is absolutely no universal answer as to which method is best. It all depends on this application itself. All right. So, here what I am performing here is a universal thresholding, and it is showing me the threshold limits here for D2 and D1. All right. It is showing which coefficients will be set to 0, and then you can say here denoise. If you just go with the default settings, sorry, and apply soft thresholding, this is what you would get. The soft thresholding gives you a nice smooth estimate, but I can choose a hard thresholding if I wish, and look at what the hard thresholding has done. If you have noticed carefully, let us go back to the soft thresholding, and I have this estimate here. The estimate here is shown in blue on the top, and compare this with what you would get in a hard thresholding. What you have noticed is hard thresholding retains the sharp features, whereas the soft thresholding smoothens the sharp features, and that is because it is shrinking. It is shrinking the coefficients which are significant as well. So, that is the prime difference. If you think that the sharp features have to be flattened in your estimate, then use a soft thresholding. If you think they should be retained as they are, then use the hard thresholding. So, that is the basic idea. Then there is something called, then of course, you can choose the way the thresholding is calculated and so on. You can choose a number of different ways, but I will not go into that. So, these are the different thresholding ways of calculating here, but I am not going to go into that. And of course, what also matters is a choice of wavelet. So, if you look at all these combinations that you have, as I said, there are enormous number of combinations, and I will give you a reference paper which has performed an extensive study on the different choice of wavelets, different choice of wave thresholding methods, and the different ways of calculating the threshold and so on. So, I will quickly give you that reference. But let me just finally go through an example of an interval based thresholding, and then we will conclude the lecture on this, the discussion with a very brief lecture, maybe for about 10 minutes.